All right, folks, here we go. We're going to talk more about properties of matter. Okay, so we divide matter into four basic components. We've talked about elements and compounds. We're going to talk a little bit more about those today, and we're going to talk about mixtures and solutions, something we haven't talked about. Matter is divided into a hierarchy like this. It's a chart that shows the two main categories, pure substances and mixtures. Pure substances, of course, being made up of elements and compounds, things that cannot be physically separated. And then the other side, having mixtures, broken into two components, homogeneous and inhomogeneous, or what we will refer to as heterogeneous. Mixtures being physical processes, pure substances involving pure or only chemical processes. So let's talk about pure substances, elements and compounds. Elements, as we've talked about, they're on the periodic table. They are only one kind of atom, right? Cannot be chemically separated into other substances. Atoms are the basics, and elements are made up of one single kind of atom. Compounds. Now, these are the chemically put together, chemically bonded substances. Okay, they can only be broken down by chemical methods. You can't physically separate a compound. You have to chemically form it. You have to chemically break it down. And when you form a compound, the new substance, it's entirely new. It has no characteristics of its two original substances. It is completely changed by those chemical bonds. Therefore, when you break it down, the pieces, they're completely different than what they were before. If you take sodium, you take chlorine. Sodium and chlorine are not good for you by themselves, but if you chemically bond them together into a compound, sodium chloride, table salt, perfectly fine to eat on your favorite foods. So let's talk about mixtures. Mixture is matter that is physically put together, therefore it can be physically separated into its component parts. The big deal here is that all the separate pieces retain their identities, they retain their properties. So here we have a sandwich that might represent a physical mixture, a mixture. We've got our bread, tomato, lettuce, cheese, right? Some meat, probably. And all of these different things still retain their flavors. That's why we put sandwiches together the way we do, because we like those flavors as they taste some way together. Okay, but this is not a chemical bond, so there is no chemical change. It's only a physical something put together. They retain their properties. In a mixture, in a physically put together thing, they retain their properties. And once again, we can separate a mixture. This salad here is a mixture. We can separate it physically. We can pick out its component parts. So we can take the lettuce, pick it out. Here we got a lettuce. We can take these beets, pull them out into the beets. And the carrots that might be in there hiding, you can pull those out as well. Okay, so we can continue to separate physically a mixture until we can't physically separate it anymore, and then what's left must be a pure substance. If it can't be physically separated anymore, it must be a pure substance. All right, two kinds of mixtures we're going to talk about. You've probably heard these prefixes before, hetero and homo. Heterogeneous and homogeneous mixtures. A heterogeneous mixture is not the same from place to place. Okay, so like our example here of a chocolate chip cookie. If I take a bite here, big bite, right? I get 3 chocolate chips. But then if I just take a bite here, I can get 0 chocolate chips. So every bite is going to be different. That is why it is heterogeneous. It's different in different places. Okay? Other things might be gravel. You pick up a handful of gravel, you're going to have some big rocks, some small rocks, maybe some sand, right? But it's different everywhere, which is the opposite of homogeneous, which is the same everywhere. When you drink your Kool-Aid or your Coca-Cola, you expect it to be pretty much the same everywhere. Every sip should be the same if it is a homogeneous mixture, which is what you want. Okay? But remember, every part in a mixture, a physical mixture, every part still retains its properties. You expect the chocolate chips to still taste like chocolate, whereas in a chemical compound, if you put two things together, you would not expect them to retain their properties because they do not. You get an entirely new substance. But here in a mixture, a physical mixture, you get the properties are still there. The chocolate still tastes like chocolate. In your Kool-Aid, the sugar that you mix in there in that mixture still tastes like sugar. The strawberry still tastes like strawberry. Otherwise, it wouldn't make any sense to drink it. All right, so let's talk about special kinds of mixtures. Solutions. Special kinds of mixtures where you have one thing called the solute that dissolves into another thing, the solvent. One substance into another. All right, like I said, the solvent is the most abundant substance, okay? The most abundant. So if you have sugar water that you're mixing up, the most abundant substance is going to be that water. The solute is the least abundant substance, okay? That's going to be your sugar. Should be easy to remember. Solvent, right? It's got more letters. It's the most abundant. Solute, less letters. It is the least abundant. Once again, sugar water, right? Water is the solvent, and sugar is the solute. It's what's going into the solvent. Solute goes into the solvent, okay? But every solution is not just a solid dissolving into a liquid, right? Here we have steel, okay? A solution which is going to become a solid. So you have two solids dissolved into each other. Iron, which is the solvent, the main component, and then you have carbon added in as the solute to make it more strong, and that is why we have steel, which is much stronger than iron by itself. Air is also a solution of gases. You have multiple gases mixed around together, but it is a solution. You expect it to be the same everywhere. All right, once again, it's a special kind of homogeneous mixture. Solutions are a special kind of homogeneous mixture, right? Can occur in multiple states of matter, right? Different states of matter. Solids can go into liquids. Liquids can go into liquids. Gases can go into other gases. Solids into solids. And liquids into gases, such as water vapor, right? So multiple different states of matter can be involved, and a solution is a special kind of homogeneous mixture. All right, let's talk about conductivity. We talked about properties of metals. Metals are conductive, okay? They are good conductors. Well, the solvent of a solution may not be a good conductor, okay? But when we dissolve certain solutes into certain solvents, they produce ions. And we know that when ions are produced, electrons are moving around. So if electrons are moving around, this is a possible mode for electricity to travel. Okay? So if you have a solution that's going to conduct electricity because of those ions, we call it an electrolyte solution. Okay? The compound that goes in the solute, right, it's going to produce ions as it is dissolving, as it is mixing around in that solvent. It's going to produce some ions. Okay? That solute is called an electrolyte, which is why a solute that is an electrolyte into a solvent is an electrolyte solution. Okay? So we have those electrons moving around, which means it conducts electricity. Okay, so some solutions called electrolyte solutions can conduct electricity, right? Strong electrolyte, right? It's going to lose a lot of electrons, make it very conductive. And a weak electrolyte, it will not dissolve all the way. It will not produce tons of ions. It will be a weak conductor. All right, so let's talk about concentrations, right? The concentration is the amount of solute that is in the solvent. Okay, we can express this idea in several different ways. You've probably heard about dilute and concentrated, right? Especially when we're talking, like, you might buy concentrated orange juice in the grocery store, and then you might dilute that concentrated mixture into more water to create your drink, right? So a dilute solution has small amounts of solute, and a concentrated has large amounts. So when we take our concentrated orange juice, it has large amounts of orange juice, very little water, and then we put that into more water, and it will be a more dilute mixture because there will be more solvent. Okay, we can also speak to levels of concentration. Okay, is it unsaturated, which means more solute can go into that solvent? Is it unsaturated? which means we can add more. Is it saturated? Okay, have we got the most we're going to get in there? Or is it something special called supersaturated, which means we've probably got too much solute. Well, we definitely have too much solute. There's more than there's supposed to be, and we've gotten that because we've done it at a higher temperature. We've heated up that solvent. We've caused the particles to move around faster, opening up more space than should be there for our solute to dissolve in there. Okay, you may have done an experiment with this in elementary school where you heat up water and you dissolve as much sugar as you can get at that high temperature, and then when it cools down, all that extra solute that shouldn't be in there, it's going to come out and it's generally going to form crystals. That's how we make rock candy. Okay, we heat up that water, dissolve too much sugar in it, and then you'll drop a little string in that water, and as it cools, those crystals are going to form on that string, making delicious rock candy. Food science, you gotta love it. All right, now we're going to talk about percent composition. Okay, that means how much of the solute is there in that solvent, and we're going to be specific now. Specific. Those other ones were kind of relative. This one's going to be specific. It's the parts of solute per 100 parts of solution. We're talking about per 100, which means it's a percent, right? That's why it's called a percent, because it's per 100. So we're going to determine the mass of the total solution. Remember, we use the triple beam balance for mass. And then we're going to determine the mass of the solute that is in there, right? We divide that out, multiply it by 100, and that is our percent composition by mass. So if I have 10 grams of sugar and I dissolve that into 100 grams of water, or make a total solution of 100 grams, then my percent by mass will be 10 over 100. Multiplied by 100 means it's 10%. That will be a 10% sugar water solution. All right, now how fast do things dissolve into other things? Well, that's determined by 4 major factors. Temperature, stirring and shaking, crushing, means basically we're determining a different surface area that is in contact, and the amount of pressure. Okay, temperature. Like we said before, if we heat particles, they move faster, which means that solute can be carried off by more solvent. Okay, here we've got some green solute mixed in a lot of yellow triangle solvent. We're going to heat that up, and those triangles are going to move faster and faster, carrying those solute particles around much quicker. So the hotter something is, if we heat it up, we add energy, those particles move faster, therefore they dissolve faster. Okay, what about if we shake it up, right? Lots of us shake or stir something that we want to make our mixture with. Like sometimes when you buy stuff at the store, right, the mixture might settle out to the bottom, so we got to shake that up and cause it to dissolve very quickly. Okay, the more you shake it, the more those particles are moving around, once again, moving around, bumping into each other, and then they'll start carrying that solute off. So the more you shake it, the more you stir it, it's going to dissolve faster because those particles are moving faster and they can be dissolved more easily. Crushing, okay? If you crush something, think about it. The more contact that the solvent has with the solute, the easier it's going to be to mix. Well, here in this cube, it's a sugar cube, colored red. Here, you're only in contact with these outside parts. That means all of the sugar in the middle is not in contact with the solvent, which means it's not able to be carried off. But if you crush it up, then all that sugar in the middle is now exposed to that solvent, which means it can dissolve much faster. So that the smaller the pieces, the faster it dissolves. And here's a good illustration of that, right? You've got this one solid chunk. These can't get in there. But here, when you break it up, they can easily, all those solvents can get in there. And pressure. Okay, look at this guy. He's pushing that particle in there. right? So if you put it under pressure, you're basically forcing those molecules of solute into the solvent. So you put a lot of pressure on these and they get in there. And they get in there. So the more pressure you apply,